Okay, here we go. Hopefully this is the last recorded notes for the year. Let me make sure we are on the screen. We are ready to rock. This is the first half of chapter 3, which is Stoic. We're finally getting to real chemistry and balanced equations. Stoic and balanced equations. I'm going to attempt to have amazing handwriting today, as you cannot see the ion equations. So let's start out with our balanced equations. For our balanced equations, there's basically five types that we learn from freshman year. The first type is synthesis. Whenever it is a synthesis equation, there is just one product. So it's two things together making one. That looks like cone product. Great. That's one product in parentheses, just to let you know. So general form would be A plus B yields AB. Or if I took something like hydrogen, which is a diatomic, plus oxygen, which is a diatomic, and I use electric and I electrify that as a catalyst, I could actually make water. That's not balanced, so I put a coefficient of 2 here and a coefficient of 2 there, and that is balanced. Speaking of diatomics, elements that never exist by themselves in nature, that is H2, O2, N2, F2, Cl2, Br2, and I2. If you look at your periodic table, besides hydrogen, it's literally the upper right-hand corner of the periodic table called the diatomic corner, which are all of your diatomics. The second type of the 5 types of reactions is decomposition. Decomposition is where you only have one reactant. So this is where one thing breaks into two. So I have AB yields A plus B. So this would be something like magnesium oxide. Magnesium oxide would break into magnesium plus oxygen gas. Magnesium plus oxygen gas, but oxygen's a diatomic, so it's O2. To balance that, I put a coefficient of 2 here and a coefficient of 2 here. When you are balancing equations, I suggest doing it in this order. First, step 1, balance metals. Step 2, balance nonmetals. Step 3, balance H. And step 4, O. Any H's and O's by themselves, balance those last. It will help you with your balancing. So that's 2. Third type of the 5 types of equations is single displacement, and it kind of is what it sounds. So one thing is getting displaced for single displacement. There's 2 types. So for a metal single displacement, it's going to be something like E positive plus AB positive negative, this matters, yields EB positive negative, because I have to have the cation first, plus A getting kicked out by itself. Or if it's a non-metal, here's my non-metal N, which is negatively charged, plus A positive, B negative. That's going to give me A positive, N negative, plus B minus. So you have to keep your cation and anion together. So an example for this would be ZnCl2, zinc chloride, plus sodium. I know that sodium's a positive, zinc's a chloride, so those are going to switch spots. So that's going to give you NaCl, because that's a +1, that's a -1, plus zinc by itself. Metals by themselves are just by themselves. You don't put any subscripts, anything like that. The only time you have subscripts on individual elements are the diatomics. To balance it, I'd put a 2 here and a 2 there. That's single displacement. Number 4. A fourth type is double displacement. So double displacement is where two things are switching spots. So if I have AB plus CD, that's going to give AD plus CB. So I could say something like this, where I would write silver nitrate reacts with sodium chloride. At this point, you should be able to write the reactants, write the products, and balance it. So I would suggest pausing at this point and trying to do it on your own. Okay. I know a lot of you probably didn't pause it and just want to see the answer. That's fine. So, silver nitrate. Ag is a +1, nitrate's a -1. That's a perfect match. Sodium chloride, +1, -1. Perfect match. Silver and sodium are going to switch spots, or it doesn't matter. The negatives can switch spots. It'll give you the same thing. That gives you AgCl plus NaNO3. The order of these compounds doesn't matter. The order within has to be AgCl, NaNO3 does matter. So that's double displacement. Okay. I gotta flip the page. Number 5 is called complete combustion, or just combustion. But the more correct is complete combustion. So combustion, the form is any carbon and hydrogen compound. So I have CXHY plus oxygen, because I have to have oxygen to burn something, gives me carbon dioxide plus water. The cool thing about combustion is the underlying part, the O2 yields CO2 plus H2O, is always, always, always the same. The only thing that ever changes is the subscript X and the subscript Y. So if I had something like CH4 plus O2 yields CO2 plus H2O. Whenever you're balancing a combustion, I suggest going carbon, hydrogen, oxygen. If you do it in that order, the right side always starts out as 1, 2, 3. 1 carbon, 2 hydrogen, 1, 2, 3 oxygens. The left, I have 1, 4, 2. So to balance this, I need 2 H's over here. That changes my H's to 4, changes my O's to 2 plus 2 is 4, which means I need a coefficient of 2 here, oxygen of 4. That is balanced. So that is balancing equations, the 5 types of equations. Very, very, very short intro. Okay. Next, here comes real chemistry. In chemistry, the mole, put a box around that because it's so important, is always the goal. The mole is always the goal. So what is the mole? The mole is a fixed quantity. All right? We need the mole because atoms and molecules are so tiny. Atoms and molecules are so, so tiny. So, let me give you just an example. Carbon has an atomic mass on the periodic table of, right here, 12.011. And I do 3 after the decimal, and that's what I want you guys to do. 12.011 atomic mass units. Well, this is how much 1 mole of carbon would weigh. And an atomic mass unit is literally just grams per mole, which means that 1 mole of carbon is equal to 12.011 grams of carbon. So the mole is just a conversion factor to go between mass and also with particles. The other thing you have to know for moles is Avogadro's number. Avogadro's number is equal to, I don't know why I'm doing it down here because I need a little bit more space, 6.022 times 10 to the 23rd. There's 6.022 times 10 to the 23rd in 1 mole of anything. So a mole of basketballs, there's 6.022 times 10 to the 23rd basketballs. A mole of M&Ms, there'd be 6.022 times 10 to the 23rd M&Ms and a mole of M&Ms. In particles of carbon, 1 mole of carbon is equal to 6.022 times 10 to the 23rd particles of carbon, which is also equal to the original 12.011 grams of carbon. So you can see how the mole is just a conversion factor. So I can go moles to mass. All right, I can flip that. We're going to be mass on the top, moles on the bottom. Or I can go moles to particles. Or I could flip that as well. So I could ask you something like, what is the molar mass of CO2? So you'd have to use your periodic table and add up all of your stuff. 1 carbon and 2 oxygens. So 1 carbon is equal to 12.011 grams. I have 2 oxygens, which is equal to 15.999 grams times 2. And you have to add that up. This is actually one of the molar masses you're going to have memorized really soon. But the molar mass ends up being 44.009 grams for CO2. So on your own, try this. Try CuNO3 parentheses 2. So add that on your own, pause, actually do it, and then check your answer in a second. So pause the video now. Okay. The correct answer, you should have ended up with 187.554 grams. 187.554 grams. Here's the thing though. The thing is that in AP Chem, especially in the 1-period version of AP Chem, we don't have time. We do not have time to be doing that. We don't have time to be adding up every single molar mass. So I'm going to assume that you guys know how to do this. So tomorrow when you walk into class, you're going to be getting this sheet, which has pretty much the molar mass of almost every single compound that we will use in AP Chem. It's kind of a magical day when you get this, but you will be getting that tomorrow when you enter class. So as long as you can do this on the AP test, I'm going to assume you can, you're good to go. Okay, so let's actually apply this. So you could see, what is the mass of 2.17 moles, and mole can be written MOL or MOLE, of NaOH. So when you're doing this, you always start with the last thing you're given, So I'm going to start with 2.17, and you have to have all these labels. Mole of NaOH. If I have moles on the top of the first step, I have to have moles on the bottom of the next step. So 1 mole of NaOH is 2 molar mass of NaOH. So when you get this tomorrow, sodium hydroxide, actually I'll try to hand this to you after the test so you have it tonight, is 39.997 grams. So this is 39.997 grams of NaOH. I'm going to type it into my calculator. So multiply everything on the top. So I have 2.17. Oh, for a second I thought I forgot to hit record. I'd have been so mad. Times 39.997 equals, there's my answer. I look at my number for sig digs. So I started with 3 sig digs, so I have to end with 3 sig digs. So my answer is going to be 86.8 grams of NaOH. Box your answer. And you can see moles of NaOH cancel, leaving me grams. Okay, what about this? How many atoms, this is different than molecules, how many atoms of Mg are in 14.26 grams of Mg3 PO4 parentheses 2. How many atoms of Mg are in 14.26 grams of Mg3 PO4 parentheses 2 magnesium phosphate? Try it, and then I'm going to show you the right answer. All right, here we go. So I have 14.26 grams of Mg3 PO4 parentheses 2 times the molar mass of magnesium phosphate. So I've got it right here, 221.551. Wait a second. 262.855. So that's 262.855 grams of Mg3 PO4. And yes, you have to have all these labels on each step. In 1 mole of Mg3 PO4 parentheses 2 times, now I need to go to smaller, so I need to go 1 mole. You can see why the mole is so important. 1 mole of Mg3 PO4 parentheses 2 is equal to 6.022 times 10 to the 23rd molecules of Mg3 PO4 parentheses 2. And I know that for every 1 molecule of Mg3 PO4, oh crap, we're out of room. I'm probably going off the screen too. For every 1 molecule of Mg3 PO4 parentheses 2, I have 3 atoms of Mg. How do I know? Well, subscript 3. I have 3 atoms of Mg. So in my calculator, here's how I would do it. I would type in 14.26 times 6.022. I like to use the EE button, 23, because that does order of operations for me, times 3 equals, divided by 262.855 equals, and there's my answer. I started with 4 sig digs, so we need to end with 4 sig digs, and that gives me 9.801 times 10 right here to the 22nd atoms of Mg. Please on the test don't stop at molecules if I'm asking you to go all the way to atoms. It's just one more step. That's basic stoic. The next thing we do is, with our stoic, is actual chemistry. So percent composition, and empirical formulas. Present composition and empirical formulas. So let me define an empirical formula for you. An empirical formula is defined as the simplest whole number ratio. The simplest whole number ratio of elements in a compound. So similar to what we were doing last chapter, but really not. In other words, it's just a mole ratio. So this is the definition of empirical formula. So we're going to come back to that. I just wanted to define empirical formula. But let me do percent composition first, and you'll see why. I could say, what is the percent composition of H2SO4? So what is the percent composition of sulfuric acid? So, first of all, an equation is always percent equals part over total times 100. So, I have 2 hydrogens, so I would do 2 times hydrogen's mass, which is 1.008 grams, times the periodic table. 2 times 1.008, so that is 2.016 grams of H, divided by the overall molar mass of sulfuric acid. Sulfuric acid is 98.078. 98.078 grams of H2SO4. Grams are going to cancel out, times 100. I would suggest solving that, pausing. After you do that, you should end up with, I like to round these just to 1 after the decimal, 2.1% hydrogen. Then I'll do the same thing for, I don't know, sulfur, because there's just 1. I'm going to take my 32.066 grams of sulfur divided by the total mass, which is still 98.078 grams, times 100. And for sulfur, I get 32.7% sulfur. At this point, you could do the same for oxygen. You could do 15.999 times 4 divided by 98.078, or you know these percents have to add up to 100. So I would just subtract, and I would do 100 minus 32.7 equals minus 2.1 equals, and that gives me 65.2% oxygen. So that is your percent composition of a compound. You just take part divided by total for all of them, and that's how you get percent composition. Okay, so if I gave you something like this, I'm going to turn the page actually. If I give you something like this, if I said a compound is made up of 26.57% K and 35.36% Cr and 38.07% O, and hopefully you figured out those all add up to 100. It has to, or this won't work. I could say, what is the empirical formula? In chemistry, a lot of the times we have to make assumptions, and if we know all of these are parts of a whole, we can assume that these are percents adding up to 100. These can also be equal to grams. So I can say if it's 26.57% potassium, I can also say it's 26.57 grams of potassium. and I can say that it's 35.36 grams of chromium. And I can say it's 38.07 grams of oxygen. I'm going to convert all of these to moles. This is what we were talking about on Monday. So times 39.098 grams of potassium and 1 mole of potassium. This is the mass from the periodic table. Times 51.996 grams of chromium and 1 mole of chromium, and times 15. You might have oxygen's mass memorized before you're done with these notes. Grams of oxygen and 1 mole of oxygen. So solve all 3 of those on your own and see what you get for your moles. Then check. You should end up with 0.6796 moles of potassium, 0.6800 moles of chromium, and 2.380 moles of oxygen. And I want the simplest whole number ratio. So I'm going to divide by the smallest number of moles, which is 0.6796. So I'm going to divide it by 0.6796, divided by 0.6796, divided by 0.6796. So when I do that, this gives me 1, this gives me 1, and this gives me 3.5. But I need the simplest whole number ratio, and I can't have 3.5 in a formula, which means I have to multiply all of these by 2. So my empirical formula is, am I going to be on the screen? Yep. K2 CR2 O7. That is an empirical formula. So let's do another one. What is the empirical formula and molecular formula, the MF of compound with 10.15% carbon, and let's just do 2, 89.85% chlorine with a molar mass of 236.7 grams per mole. So what is the empirical and molecular formula of a compound composed of 10.15% carbon and 89.85% of chlorine with a molar mass of 236.7 grams per mole? I would suggest figuring out the empirical formula first, pausing, and checking your answer with me to see if you get the empirical formula correct. Then I will show you how to get the molecular formula. So do your empirical formula now. I'm going to assume it's 100 grams, so 10.15 grams of carbon times 12.011 grams of carbon and 1 mole of carbon. When I do that, I get 0.8451 moles of carbon, and I've got 89.85 grams of chlorine times molar mass in the periodic table, 35.453 grams of chlorine and 1 mole of chlorine. So that gave me, I cannot even read my own writing, 89.85 divided by 35.453. 89.85 divided by 35.453. Yeah, I got 2.534 moles of chlorine. Divide by the smallest, divide by 0.8451, divided by 0.8451. Hopefully you're doing some mental math. I know this is going to give you 1, and this should give me 3 or close to it. So my empirical formula.
Good afternoon.
Pause.
Please excuse this important interruption.
Okay, we're back. So my empirical formula is CCl3. So that's done. To get the molecular formula is just the unreduced empirical formula. So what I'm going to do is I'm going to come up with a rough molar mass of this from the periodic table. So I'm just going to do this very roughly. So I know that carbon is 12, so I've got 12. I know that chlorine is 35. 35 times 2 is 70, plus another 35 is 105. 105 plus 12 is approximately 117 grams. And I know this should be a whole number, that 236.7 divided by 117 gives me 2, which should be a whole number ratio. So to unreduce this, the molecular formula is going to be C2Cl6. So I just take my molar mass, I figure out the approximate molar mass of this, I divide it by the molar mass of the empirical formula, I have to multiply the empirical formula by 2 to get the molecular formula. So that is that. Let's do one more, just to make sure you guys got it. So here we go. A 1.214 gram compound of CXHY. Hopefully you're thinking combustion. Is combusted to produce 4.059 grams of CO2 and 0.9494 grams of H2O. Period. What is the empirical formula of CXHY? The first thing I would do would be write what I have. So I'm going to write an equation. Always try to start by writing an equation. So I have CXHY with a mass of 1.214 grams. I know it's combustion, so plus O2 yields CO2 plus H2O. And I know that I have 4.059 grams of this, and I've got 0.9494 grams of that. At this point, try to get the empirical formula on your own. Attempt it. Pause. Here's how I would do it. I know that I need to get moles of carbon and moles of hydrogen. The only place I have carbon where I can actually figure out moles is in carbon dioxide. So I'm going to take my 4.059 grams of CO2, and I'm going to get that to moles of CO2 because I can't get to moles of carbon directly from this. So there is 44.009 grams of CO2, which I have memorized, but you guys can look that up. Carbon dioxide is right here, 44.009 in 1 mole of CO2. And I know that in 1 mole of CO2, I have 1 carbon, which is 1 mole of carbon. That will get me my moles of carbon. At this point, you should be able to pause and try and finish it to do the rest. So I'm going to solve that, and I get 0.09223 moles of carbon. The only place I have hydrogen where I can do some kind of math with this is water. So I'm going to take my 0.9494 grams of H2O times water's molar mass, which is 18.015 grams of H2O. You'll have that memorized pretty quick. And 1 mole of H2O. And I know in every 1 mole of H2O, I have 2 moles of hydrogen, because subscript 2 means 2 moles. Don't make that mistake where you forget to take the subscript and make that a 2. This gives me 0.1054 moles of hydrogen. Now I've got it. Divide by the smallest. So divided by 0.09223, divided by 0.09223, and this gives me 1, and this gives me 1.14. Well, pooey. Now you have to start taking 1.14 in your head and seeing what that multiplies into a whole number. Because your brain is probably done by now. Some of you are good with mental math. I'm going to tell you, if you multiply this by 7 and this by 7, you will have whole numbers. So, carbon is 7, and this becomes 8. So my empirical formula is C7H8. If you understand this much chemistry, you are prepared to do the lab for the next 2 days. After this, the goal is to go back to live notes on Friday to talk about limiting reactants, stoich, and all that jazz. Hopefully you've enjoyed all of these online notes. I think it's going to be very helpful to go back to live notes starting on Friday. Have a great day, and go Woo.